Hi, we are SKA Robotics, a division of Student Space Association from Warsaw University of Technology. Our team consists of students from various faculties of our university. Today, we want to show you the progress we have made with our Series 2 Rover. Our team consists of 29 students from various fields. We are divided into 3 sub-teams: mechanics, electronics, and software. Each of those is overseen by a coordinator, a more experienced member of our team whose job is to oversee the progress and solve any potential problems on case-by-case basis. Group's efficient cooperation is ensured by the Chief Technical Officer. Chief Financial Officer and PR Coordinator are also elected from our team to further relieve the team leader from excessive workload. This system has proven itself as an efficient way to facilitate the division of work and to achieve reliable results.
Our rover uses a system designed and built by our team. It consists of an unusual copper beryllium suspension designed by the usage of FEM optimization, along with 3D printed wheels created after weeks of field testing different versions of those. All this allows us to traverse through difficult, rocky and sandy terrain with ease. Thanks to a camera backend which uses WebRTC, we are able to simultaneously stream video from multiple cameras, with automatic compression quality selection. Our control interface is a website built with Vue.js, hosted on the main computer of the rover. It is centered around a modular drag-and-drop window system, which allows for great flexibility and expandability. This solution gives us a very robust control over the rover and allows us to visualize its state.
The autonomous navigation system developed last year facilitates a SLAM solution by Spectral AI for visual odometry and occupancy map construction. SLAM data is fused with multiple other sources, such as GNSS module and an IMU, to ensure that the system is resistant to drift and tracking loss. The GNSS module uses PointPerfect, a PPP RTK GNSS correction data service by uBlocks, in order to vastly improve the position accuracy down to 3 cm. Object detection is based on an artificial neural network trained on a custom dataset which consists of photos taken in different locations, light conditions, and with different cameras. In addition, by utilizing classical computer vision algorithms, we detect and determine the relative position of Aruco markers. This process involves detecting the marker's corners, estimating its pose, and calculating the distance based on the known size of the marker and the camera's intrinsic parameters.
For years, we have continuously improved our old robotic arm. We identified numerous limitations with that design, and for this reason, we decided it's time to build an entirely new manipulator. We have significantly reduced its weight by redesigning the structure and carefully selecting motors. Moving from linear actuators to quasi-direct drive BLDCs allows us to control the arm with better precision and dexterity. We use field-oriented control to achieve maximum torque at low joint velocities. The 120 Nm of peak torque let us easily lift some serious loads. We utilize multi-use motor controllers with custom absolute encoder boards that provide us with all the required functionality while allowing us to keep the hardware assembly compact. We have developed various methods of controlling the robotic arm: leader-follower teleoperation, VR teleoperation, as well as autonomous trajectory planning and rollout with MoveIt library.
Mini quadrocopter ICAR has been joined by our new design, equipped with even more advanced systems. After a series of accidents and design errors, we brought ICAR to a state in which we can use it in everyday experiments. This fact motivated the team to prepare a new design equipped with advanced components such as a deep camera, infrared lidar, and precise IMU sensors. Thanks to this, we are able to develop advanced algorithms for position estimation, obstacle and object detection, path marking, and terrain mapping using a drone.
The design of the science module involved taking samples from 3 different locations. For this purpose, 2 devices have been designed: a drill capable of taking samples from the surface and depth of up to 15 cm, and a manifold, transferring the excavated soil into conical flasks. The drilling subsystem is based on a proven solution tested at 3 competitions. Its operation consists of drilling with a screw rotating inside a cylinder, in which the soil is retained. In order to extract the sample, the module is lowered, then the sample is picked up and poured into the distributor. It is equipped with 3 separate tracks with lockable containers. On each track there is a separate cart into which the sample from one test site is filled. The cart then moves over the openings with conical flasks to place the samples in them. After collecting samples, reagents are added to the flasks and the results of the chemical reactions are checked.